Hi guys. So in the last lecture, we looked at the transistor implementation of the logical or gate. Now we're going to look at the complement of that, how to use transistors to implement the AND gates. And so let's get right to business. In the previous video, we also covered a brief introduction, or a brief recap about transistors. But in case you missed that, a transistor is a current controlled device. So it's a current controlled device. If there's a current IB flowing through the transistor, then the transistor becomes a closed circuit. If IB is equal to 0, then the transistor becomes an open circuit and current can't flow. So this is all we need since we're using the transistor as a switch to simulate it as an AND gate. Alright? So let's get right into business. To simulate our transistor as an AND gate, we're going to need to draw our transistors in parallel. So how does that work? We're going to need to put two transistors to directly depend on each other. Okay, so that's one this way and one that way. So these are two input transistors, and our output transistor is going to be somewhere, let's say somewhere here. All right, so how do we go about drawing this? First of all, we have to put our inputs going into the bases. Okay, that's always a good place to start. Draw your inputs going into the base of your input transistors and also into the base of your output transistor, since it's also going to have to come from there. All right, so we know this is going to be, let's call this Q1, transistor 1, and Q2 for transistor 2. This time around, we're only going to ground Q2 and Q3. So that's the output transistor. These are the only ones we're going to be grounding. Okay, so these guys are coming to ground this way and that way in such and such a manner, and we can draw a ground connection. So that's always a good place to start. Which of your transistors are being grounded? If you've drawn them in the right orientation, then you can get right into doing that. Okay, so the neat trick about transistors, using them for an AND gate, is that the collector, the emitter of Q1 is directly tied to the collector of Q2. Okay, so that's how they directly defend each other, so that they are connected in parallel. All right, so then we take the collector of Q1 high, then we know we're going to raise this to 5 volts. But for that, we definitely need to add a load resistor. Without the load resistor, we won't get the voltage drop we need. Okay, so we put our load resistor, and then we draw our circuits, and then from this node of our load resistor and Q1, we take that right into the inputs of Q3. Okay, that's this way and that way, and then the same thing happens on this side. When we're going to raise this up to positive 5 volts, but it's going to need its own load resistor. Okay, so this is a rather big circuit where you can make rather tall circuit. You can make yours shorter as need be. So let's call this M for output. All right, let's call this junction N. Okay, so let's say junction M output X. Right, so this is going to be A, and this is going to be B. We're drawing an AND gate, so this is raised to positive 5 volts. All right, let's call this R1 and call this R2. Okay, we're dealing with NPN transistors, so it's important to put these arrows pointing towards the emitter. Okay, so that looks cool. We're dealing with an AND gate, so let's draw the AND truth table so we don't lose track of whatever we're handling. Okay, so now we're going to have inputs A, B, and output X. So let's call this A, B, and output X. The AND gate configuration is very simple. It is high only when both of its inputs are high. So that's going to be 0, 0, 0, and a 1. So we have to ask ourselves, since we've drawn our transistor implementation like this, how do we analyze this circuit to make sense of this being the AND gate? Okay, so let's get to work. For the first case, when both A and B are low, so A is low, B is low. Okay, so we can even start by writing out what we can tell. So for case 1, A is low and B is low. All right, so A is equal to 0. A and B are both equal to 0. What does that mean? That means that A and B are equal to 0, That means the current flowing into the base of Q1 and Q2 is also 0. There's no current into this base, and there's no current into this base. That means that transistors become open circuits. This guy turns off. This guy turns off. All right? So remember what we said. Since N is now floating, there's no way to connect N to ground. Then it assumes the voltage of whatever is raised to. So that's positive 5 volts. So that means N is being raised to positive 5 volts. Okay? That is a positive voltage. That means some current enters the base of Q3. Okay? So some current enters the base of Q3 and turns on this transistor. So Q1 is off, Q2 is off, and Q3 turns on. Since this transistor is turned on, then it forms a closed circuit all the way from junction M after R2 connected to ground, which is at 0 volts. Okay? So since this is connected to ground and there's no load from M to ground, that means node M is also at 0 volts. So recall, node N is raised to 5 volts because both of these are open. Node M is dropped down. Node M is dropped down to 0 volts. So that's 0 volts since transistor Q3 is active. And since it dropped down to 0 volts, that means X is also equals to 0. Okay? It's very simple. So Q1 is off. So Q1 is off. Q2 is off. And Q3 is on. Okay, in that manner, because there's current flowing into Q3. So that's how to understand the first case of the AND gates. All right, A and B are 0. This is 0. This is 0. No current enters IB. No current enters IB. This guy stays turns off. This guy turns off. N is a floating node. Remember what we said? If I have a voltage, plus and minus, over some resistor, and there is no way for this guy to connect to ground, no matter what this voltage is, if this is 30 volts and this is R4, then since this is not connected to ground, since this circuit is not closed, then the voltage here is the same as the voltage here, 30 volts, all right? It's open circuit voltage. That's how this works. So that means N is also at the open circuit voltage of positive 5 volts. So that positive 5 volts enables some currents to drive into the base of Q3, turning on the transistor, grounding M, and making X equal to 0. All right? So we can do it for the remaining scenarios. We handled when Q1 and Q2 are off. So let's look at what happens when we turn on one of them. So let's look at case 2. So maintaining our circuit. So that's A is equal to 0. And B is equal to 1. All right? So let's look at what happens. A is equal to 0. B is equal to 1. What does that mean for us? A is equal to 0, which means that there is no current flowing into this base. This transistor is off. B is equal to 1, meaning that there is some IB flowing into the base of Q2. Okay? This transistor is on. Cool? But what does that mean for us? This is an open circuit. And this is a closed circuit to ground. Regardless, once there's an open circuit in this connection, there is still no way for N to reach the ground. So that means N is still going to be raised to positive 5 volts. All right. So even though B is on, because there's an open circuit across A and these guys are connected in series, okay, so the AND gate is the series. The AND gate is a series connection. Okay, and the OR gate is a parallel connection. I believe I misspoke earlier. Okay, so since these guys are connected in series and there's an open circuit along this path, then this means that N is still floating and is raised to positive 5 volts. N is positive 5 volts. There's some base current entering here, and Q3 turns on. All right. So M drops down to 0 volts. Since there's a straight uninterrupted path to ground from Q3, and since M is dropped down to 0 volts, then voltage on X is equal to 0. Okay. So Q1 is off. So Q1 is off. Q2 is on. And Q3 is on. All right. So even though Q3 is on, M is dropped to 0. The voltage at X is still 0, which is what we aim to get with our circuit. Okay. So let's look at it and do for our third case. Turning A on and keeping B low. Okay. So we raise this. and work with a blank slate. Case 3. A is high and B is low. Okay? What does that mean for us? So now that A is high, this is 1 and this is 0. We know that no current enters Q2. This guy turns off. Some current enters here. This guy turns on. Alright? So closed circuits, open circuits, ground. As long as there's an open circuit in that connection, there's no way for N to reach ground. So N is still a floating node and is raised to 5 volts. Okay? Same thing applies. M drops to 0 volts, X is equal to 0. Okay? Q1 is on, Q2 is off, Q3 is on. Alright? So it's almost the same thing that happens in our initial connection. So now we're going to look at the last case, which is when our AND gate gives us a high output. And that happens when both of our inputs are high. So let's look at how that comes about. Okay, so case 4. A is equal to 1, B is equal to 1. What does that mean for us? That means this guy turns on and this guy turns on because there's a small voltage and there's a small current IB entering the base. Okay, so that means we have a short circuit, a closed circuit, and a ground connection. So this is one full electrical path, meaning that N can be grounded. Okay, so finally N gets dropped to 0 volts. Okay, remember now we have a closed path from positive 5 volts to R1 down to ground. N drops to 5 volts. So since N is at 0 volts, then no current enters IB. Okay, and this guy becomes an open circuit. Since this is an open circuit, M is floating and remains at the voltage as positive 5 volts. So M remains at positive 5 volts, meaning that X is equal to 1. Okay? So Q1 is on, Q2 is on, Q3 is also on. Alright, so that's the transistor implementation of the AND gate. Alright, for it to work, we need to. Okay, so that's actually, so Q3 is actually off. Okay, pardon me. So Q1 is on, Q2 is on, and Q3 is off. Okay, so that's the transistor implementation of the AND gate. Alright, remember, for that to happen, we need to connect these guys in series, and we talk about inputs and see how that affects the voltage at node N and also the voltage at node M, where output X is taken from. Alright, so that's all for now. Thanks for watching, and I'll see you in the next video.